So last time we left off with this slide here talking about tangent planes to surface level surfaces, and I want to continue this discussion. So I want to go ahead and get right into an example. Before I do, I just want to point out that this is a very simple and straightforward formula. You don't really have to do much. All you really have to do is take the partial derivative with respect to x at a specific point, evaluate it at a specific point, times x minus x sub 0, and then add that to the partial derivative with respect to y at a specific point times y minus y0, and the same thing for your z component as well. And this will give you the equation of a tangent plane to some surface. Now, there's also a normal line that comes out of the surface S at some point, and you can actually find the equation, or in this case, the symmetric equations of that normal line using these formulas as well. And they are basically derived from this tangent plane equation. And this is equation number 19. So take note of that. Let's just go ahead and do an example. You'll see how easy this is in this next example. So for this first example, let's go ahead and find the equation of a tangent plane and the normal line to the given surface at the specified point. So as we can see here, we have xyz equals 6 at the point 1, 2, 3. And first you're going to start by letting your capital F of x be equal to xyz. Now we could let it equal to xyz minus 6. Basically, you could set this original equation equal to 0. But as you'll see in a moment, we're going to be taking the gradient of f. And as we all know, the derivative of a constant is 0, and that's going to go away anyway. So that 6 doesn't matter really what number's here. Any constant's really going to be gone pretty soon. Even if this was 6 million, once we take the gradient, any constant will disappear. Sure enough, we take the gradient. You'll notice that we take the derivative with respect to x for the first component, the derivative with respect to y for the second component, and the derivative with respect to z for the third component. Now once we do that, we plug in our specific point, 1, 2, 3, and we get this value right here. Now, something that we should know is that once you have this value, you're essentially finished. Basically, all we need to do now is provide ourselves the derivative with respect to x, derivative with respect to y, derivative with respect to z, and evaluate at this point 1, 2, 3. Well, that's exactly what this is here. 6 represents the derivative with respect to x, 3 represents the derivative with respect to y, and 2 represents the derivative with respect to z at the point 1, 2, 3. So we can go ahead and just plug in the equation of the tangent plane right away, giving us this here, which is 6 times x minus 1, 3 times x minus 2 plus 2 times z minus 3. And generally I like you guys to clean these up. You're going to give us like something like this here. And it's as easy as that. Just find the gradient, evaluate it at that point, and then plug in those direction numbers to give you your equation of your tangent plane. Now with a little bit of rearrangement, you can find the symmetric equations of the normal line. Because as you can see from the example here, for part B, they want the equations of the normal line to the given surface at the specified point. So as you can see here, the symmetric equations of a normal line to the surface are going to be very similar to, very much related to what we found in part A. And that's all there is to it for this particular question. And really, let's go ahead and do another example, even though it's almost not really worth it because every single problem like this one is done the same way. So we don't really need to do another problem. I will show another one, but I'll go fairly quickly through it. Please make sure that if you have any questions, go ahead and chat hit the chat or send me an email and let me know if you have any questions. Let's go ahead and take a look at another example. So here's another example. I got two more exactly. Let's go and take a look at this guy. So for this one, again, let's go ahead and find the equation of a tangent plane for this particular example. Now again, you can go ahead and subtract 4 on both sides and set this thing equal to 0, but again, once we take the gradient, that 4 is going to disappear anyway. So I'm going to go ahead and let my f just simply be everything but the 4. Just kind of ignore it. I just simply rewrote it, x squared minus 2y squared minus 3z squared plus xyz. Let's go ahead and evaluate this gradient here. Again, you take the derivative with respect to x, then the derivative with respect to y, then the derivative with respect to z, and you get this guy here. Once again, as you find that gradient, you simply evaluate at the number, in this case, at the point, 3, -2, -1, which in this case gives us 850. Those will be your direction numbers for your equation of the tangent plane. Now that's very interesting though, because the direction number here on the end is 0. So that means one of our components is going to be gone in a moment. You'll see as we do part A to this example, the equation of the tangent plane is going to cause us to cancel out the third component here, the z component, leaving us with the tangent plane equation of 8x plus 5y equals 14. Now, if you find I'm going a little too fast, feel free to take pictures of the screen at any moment. And also, eventually I'm actually going to send out a link to a YouTube video that can show you this video as well. So if you ever think I'm going a little too quick, it's only because I'm trying to get through the material, and that way on the YouTube video you can actually stop, you can pause, you can rewind at your leisure. Once again, as I mentioned before, the normal line to the surface at the point 3, -2, -1. It's very much related to the equation of a tangent plane. You'll see a lot of similar elements. You'll see x minus 3 is being divided by the direction number 8. Y plus 2 is being divided by its direction number 5. But then you'll notice a comma here. Very important, that comma. Very subtle, but important. But you can't divide by 0 for this direction number here. So as you recall from chapter 12, we just go ahead and leave z as z equals to -1. Great. Okay. Let's go ahead and move on to this example here. Now, this is the same exact problem as before. The only difference here, though, is that here looks like we don't have a z term. In fact, we can actually go ahead and discount the z term. This is remember, when you find the gradient, you must only consider the independent variables when you take partial derivatives. So in this particular case, what we do here can be the same as before, but only we're not going to have the z term. So, what does that mean? Well, that means I basically have my gradient is going to be simpler. It's just going to be a 2-component vector this time. So notice that my first component is y, the second component is x. And that's simply because the partial derivative with respect to x is going to be y. And the partial derivative with respect to y is going to be x. Now, we go ahead and evaluate the gradient at the point 3, 2. We get the vector 2, 3. But I want to point out something very important here. Now, let's read the question up top before I continue. It says they want us to find the gradient vector and then use it to find the tangent line to the level curve f of xy equals 6 at 3, 2. Now, again, as we're taking the gradients here, this constant's really not going to matter so much. So, but you'll see in just a moment how we can go kind of get around this to actually find our equation of a tangent line. So this time we're not looking for the equation of a tangent plane, we're looking for the equation of a tangent line. But as I mentioned in last class, the gradient will always be perpendicular to the tangent line of the surface. So because this is true, what we can simply do is set the dot product equal to 0. And the dot product of what? Well, the dot product of the gradient dotted with where the tangent line physically is touching the surface, which is at the point 3, 2. That's why I have x minus 3, x minus 2 here. And this is not multiplication. This is the dot product. And when you set it equal to 0, you are guaranteeing that it's going to be perpendicular. So we go ahead and dot product it. I'm sure we all know how to dot product. You take the 2 and multiply it by the first component here, the x minus 3. And you take this 3 here and you multiply it by the second component, y minus 2. And then, of course, we clean it up, and then that's our equation of a tangent line. So it's very similar to the previous slide, with a little bit of twists to it, but for the most part, it's pretty much the same thing. All right, to finish off this lesson, this is actually a really interesting example. I really like this one, and you have one very similar to it in the homework, like 1 or 2 of these. So let's pay close attention. The question is, are there any points on the hyperboloid x squared minus y squared minus z squared equal to 1 where the tangent plane is parallel to the plane z equals y, or x plus y? So again, we're talking about some sort of tangent plane that is parallel to this given plane here. Are there any points? Well, looking at my notes here, let me scroll up. In this particular problem, I'm going to go ahead and let my f this time equal to the hyperboloid itself. Again, I just ignore the 1. And then we proceed in the same way. Like we basically find the gradient of f, which in this case is pretty simple. The derivative of this with respect to x is obviously 2x. The derivative of this with respect to y is negative 2y. The derivative of this with respect to z is negative 2z. And this essentially is going to be our normal vector to the surface. That's what these are. So again, please don't forget that. Remember, a normal is shooting straight up into the air from the surface. In fact, let's go back real quick and remind ourselves what that is. So if I back up just a couple slides here, there's a picture here. Notice that the gradient is just shooting straight up, perpendicular from the surface itself. So don't forget that. Okay. And as we all know, a normal vector is what's needed in order to find the equation of a tangent plane. We all know that from chapter 12. I'll be coming back to that very soon. So basically, as I mentioned, this normal vector to the surface is going to be the normal vector to the tangent plane. Now, if we take a quick peek at the question again, it says, are there any points on the hyperboloid where the tangent plane to the hyperboloid is parallel to the this given plane here? And as we can recall from chapter 12, what do we know about when you have two planes that are parallel? What has to be true? So I'll ask again, what has to be true about two planes that are parallel to each other? Well, the only way you really can find two planes that are parallel to each other is if the following is true. If you recall from chapter 12, two planes are parallel if and only if their respective normal vectors are also parallel. That is the only way that two planes are going to be parallel. Now, the vectors that are physically on the planes are obviously parallel to each other as well, but there are so many of them that it's hard to tell specifically how they are parallel and what way they orient themselves. But with normal vectors, there's no question. So because of this, what I need to go ahead and prove is that the normal vector to the tangent plane is going to be perpendicular to the normal vector of the given plane, and that given plane being, let me show that again, this guy right here, z equals x plus y. So go ahead and scroll up again. If I'm going too fast, take pictures of these little notes I'm making, and we'll go ahead and continue. So notice I'm going to take this question that I was originally given, and I'm going to reframe the question. So another way to write it is, are there any points where the respective normal vectors are scalar multiples of each other? And we should know this from chapter 12. We know that if two vectors are parallel to each other, then they're going to be scalar multiples of each other. And the two normal vectors in this particular question are going to be these two guys. Now, this first one, you're probably like, okay, I already know what that is. That's the gradient. I know exactly where you got that gradient from down here below. But then you might be like, well, where's this one from? So where's this one from? Well, I'll tell you right away. Again, this goes back to chapter 12. This first part is chapter 14, but this second part is chapter 12. Where did the 1, 1, negative 1 come from? Well, it came from the fact that that is exactly what the direction numbers are for this plane right here. Okay. In fact, if we take this plane, oops, sorry about that. If we take this plane right here and just basically bring the z over to one side, you'll notice that the that the 1, 1, negative 1 are exactly the direction numbers for this equation of this given tangent plane. So that's where I got those from. So again, I'm sure everyone knew where I got this normal vector from, the 2x, negative 2y, negative 2z. But maybe you were a little rusty or not quite sure where I got the 1, 1, negative 1 from. That was from the given plane right here. Okay, so now that I have my two vectors, again, we want to prove that these two vectors ultimately are scalar multiples of each other. Keep in mind, though, everyone, that it has to still follow along with what's known as the hyperboloid here. If it doesn't follow along with the hyperboloid, then it will not work. Let's find out if it does. So, now if such a point exists, then there must be some point x sub 0, y sub 0, z sub 0, such that the the gradient vector at x sub 0, y sub 0, z sub 0 should equal to some scalar multiple of the 1, 1, negative 1. And as you can imagine, what we're going to do is we're going to go ahead and set each component equal to each other. So obviously the first component, 2x sub 0, is going to be set equal to not only the 1, but also the fact I'm going to go ahead and take this c and multiply every single component by the c. So I end up getting 2x sub 0 equals c, which if you solve for x, you get x sub 0 equals c over 2. Obviously, if you set the y component equal to the y component of the second formula, you get, again, negative 2, well, this time negative 2y sub 0 equals c, which simplifies to, or solves to, y sub 0 equals negative c over 2. And as you can imagine, the z value will also be very similar. And then what we're going to do next is we're going to take all three of these values, and then we're going to sub them into the hyperboloid equation. Now remember, we're looking to see if there are any points that can achieve a parallel tangent plane to the given plane given to us in this problem. So taking the hyperboloid equation, we plug in those values into the hyperboloid equation. We simplify. I multiply with both sides by 4. The first two terms cancel out. We end up with negative c squared equals 4, which is obviously impossible. This can't happen. Because this can't happen, we can make the final declaration that no such point exists on the hyperboloid. Okay. So that concludes section 14.6. Again, if you have any questions, please send me an email or in the chat. Thank you.